former student of Zoe, now co-supervisor. Friends, and we'll talk about the four fundamental theories of pseudofinite and other things.
Thank you very much. Great honor to be here among you all. Having known Zoe very well, I will also start with something personal. So I came to Paris after having done the first master in Bonn, but there was no model theory in Bonn. Almost not. So I came to Paris to learn model theory. So Zoe did not teach, but was at that year. But I attended the working group, and it was really very good. So I was really thrilled and thought, okay, I want to do this work with her, which I did then. I did my master's with her. She told me, and I mean, related to my talk, I should read Definable, the book. I have not really read the book. I should have, maybe, but I also diverted to other topics then. And I want to tell also the anecdote, I mean, related to Zoe's character. She told me she doesn't want to take me alone as a PhD student, because there are other students, which was Ronald, who had started a year before, was not yet so advanced in his results and so. And many years later, she told me the actual reason was that she feared that we would shout at each other this way. Oh, I mean, we shouted at each other, but it was never a fight. It was just a game who can speak louder, maybe. And I'm also very good at it, I think. So anyway, and I'm also stubborn, so. Yeah, so I did the PhD, but actually I was based in Lyon, so it was a very interesting experience, because I came to Paris maybe every other month and would just tell her what we did, because in my PhD I was working on something which was on Wagner's specialty. So, but at the very end, so my last year I spent in Berlin, and Zoe would read my thesis, but so carefully, line by line, and I would get, at that time it was still fax. So, you know what this I got like fax, 30 pages. On each page, I don't know, 20 things, and so like the text, that's of course. So that was Zoe. I mean, and then when I was a postdoc in Berlin, and I was very touched by the fact that both François Delon and also Zoe both visited me in Berlin and convinced me I should come to Paris and apply to Paris, and so I did, and came 2008. From then on, I was a colleague of Zoe's. We never worked on a paper together. We don't have a joint publication, so my talk is very different from Udi's. We talk about her work mostly, but we organized working groups, conferences also, and for some time I was a co-organizer of the GTM at the end of my time in Paris, just before François stepped out, maybe for 2 years or so. I was part of the team. Really nice, and also on time we both joined at that moment. And since I'm away, I was invited a couple of times because today is a special occasion. Yes, Zoe. Over the years, we became close friends. Even if she was also often a little bit like a parent. I mean, she would make me remarks about my clothes and my haircut. But other than that, I think we became. It was already mentioned. So Stefan Ludwig was also here. Is a joint PhD student we took together, and it was a real pleasure to co-supervise with Zoe. I saw how she works as a supervisor from the other side of things. Okay, so what will I talk about today? Talks will be very different from this. So maybe yeah. So here's a plan. So I want to talk about another strand of Zoe's work, which basically all her mathematical life was on her screen as well. So it's KC fields, and in particular pseudofinite fields. Certainly her main work is the work we talked about, and the series of papers on different fields. And I think, well, yeah, but it's also closely related in techniques, in questions, and she did a lot on PSC fields. And you will not see the whole picture, of course not, but I chose a couple of highlights maybe, and dared to omit. So please, miss, or I will only talk about a couple of things, and I will give also definitions and things. So it will also be mathematically proper. Maybe you can take something home even if you don't know so well. Okay, so first, after the intro, I will talk about Zoe's work on the finite fields. You will see her work with Cherlin and Macintyre, very influential work in the early 90s. And then a big topic in her work is like around amalgamation. We have seen this talk, free amalgamation is an important feature. And then in the fourth part, I want to talk about a paper she wrote rather recently with Nick Ramsey. I had also suggested that Nick would be a nice speaker for the second part because he's one of the latest collaborators with Zoe. He's not here today. And at the end, because I thought about Zoe, she would maybe not like that it's only an homage to her, but also to see some new mathematics. I will mention a little observation which is joined with Udi on definable types and pseudofinite fields. Just because I had asked a question to Zoe and to Udi at the time years ago, and there is a partial answer to this. Okay, let's go into it. So the main player is pseudofinite fields, pseudo-algebraically closed fields. So definition is easy. Every absolutely reducible variety over the field has a rational point. So they were introduced by Ax in his influential paper on pseudofinite fields, where he studied the variety of finite and pseudofinite fields. Well, one can say he studied the pseudofinite fields in order to understand the finite fields AB. Not completely wrong. You need to study the infinite models. They were also called regularly closed, but this disappeared a little bit. But actually, this would be a very good terminology because of the last point here, number 4, for characterization. So the field is PAC if not just you have one point, but in every absolutely reducible variety you have a statistically dense set of points, because you can always take away some proper subvariety and you still find a point, so it must be dense. And you can also reduce to curves, but even better, you can reduce to plane curves. So you only need a number 3, which is any plane curve, which is absolutely reducible. So the polynomial defining is reducible with the algebraic closure. Every such plane curve has a k-rational point. That's enough. You just use Bertini to reduce dimension, and then you use the primitive element theorem to get the plane curve. Proof. And 4 is a monotheoretic characterization, namely you are existentially closed in every regular field extension. This is by saturation, you get it from statistic density for number 2, for example. So you can, what does it mean, existentially closed? It means every quantifier free formula with parameters from the little one having a solution in the big one has already a solution. And this is equivalent to, you can embed the bigger one into an elementary extension.
If you have a separately closed field, then clearly it satisfies some of the criteria. But if you interpret absolutely reducible, it depends what you mean. But if it is absolutely reducible in the sense that it remains irreducible, not necessarily integral, you mean probably absolutely integral.
Geometrically. I mean, over there, by closure, it's irreducible.
No. Reducible and reduced.
Okay, you're right. You're right. I mean, as a set of points, you're right. I mean, as a set, yeah. You're right. You're right. Okay, so what is a pseudo-finite field? It's an infinite model of the theory of all finite fields. So by compactness they exist. And, well, note that the class of PAC fields is elementary by what we thought before. Every polynomial, every polynomial to variable which is absolutely reducible has a 0. This can, for example, be said. You can also use the other factorizations, but it's a bit more difficult. And some sources, algebraic extensions of PAC fields are PAC. This is very restriction. And importantly, using the Langmuir estimates, which I will talk about in a second, it follows that every infinite subfield of the algebraic closure of a prime field is PAC, and also any pseudofinite field. And another source that comes from is a probabilistic result if you have a countable divergent field. For example, the rationals, you take the gamma group of the field to the E with the H measure, then with probability 1, the fixed field of a couple will be both C and have the generic alpha group, which is the free, finite free group on each generators. So that's another source for C fields. Okay, here are line weight estimates, so which go into axis characterization of pseudofinite fields. Given natural numbers m and e, there is a constant depending on these. So over every finite field, and every variety which is absolutely reducible defined, say M space defined over that field by polynomials of degree at most e, you have the count. It's approximately q to the d many points, where d is the dimension, the algebraic dimension of the variety. So when q goes to infinity, it means that the set of the number of rational points of d must be non-empty, because on the right-hand side the exponent is d minus 1/2. So the growth rate of the left takes over for large q. So Marx used this to calculate pseudofinite fields, just as the perfect fields which have the right number group, the finite field, so these two are elementary. And the third fact is, yes, by the way, the only non-trivial thing you can say about a finite field in the large is line weight. This is a philosophical way of looking at this. Everything that follows for large finite fields follows, everything which is non-trivial, non-elementary, follows from this line weight. So it follows the decidability of pseudofinite fields and also of finite fields, with a little bit of extra work from this. And there's some quantifier reduction, which was also mentioned in Udi's talk. For difference fields, you have these finite covers. It's the same for pseudofinite fields. One has to understand if you have two pseudofinite fields, F1 and F2, they have a common subfield. Then the two are elementary equivalent over the common subfield if and only if the algebraic closures are isomorphic, the relative algebraic closures. That means, in terms of quantifiers, that you need to understand finite covers of a variety. Bounded existential formulas. That is what the second point says. You have two tuples from the pseudofinite field. In B, the n tuples, they have the same type over E if there is an isomorphism in A to B, but not just of the fields, but of the relative algebraic closures. That is analogous to what we have seen in ACFA before in the first talk. Okay, now this was intro for pseudofinite fields, so I hope we're all on the same page. And so most of you know this of course by heart, but we said it. So those work. So when Christian Delbel visited me recently, he showed me this paper of Zoes from '89, and I thought I have to mention it quickly here. So an early paper of Zoes addressing the question of Laus. She looked at the Artin-Schreier map. So you have FP Alt, Artin-Schreier goes to FP Alt, and you want to have a section of this map. So this is the same thing as naming a complement FP vector space of FP, because FP is the kernel of the map, so I need to name a complement. And what she did is very, what she did, she works in this language where you add a predicate for a vector space, called V. And you look at structures, which is a field of characteristic P, which is decomposed as FP direct sum V. Fields of characteristic. And she shows that it's a model companion, which is equal to a model companion of the situation where you add a section to the Artin-Schreier map. This is very easy and standard model theory, but then she did something. She showed that on the algebraic closure of FP, there is a V which satisfies this actual maximum. So what she showed, that's this part is elementary. you know how to do such things, you do this in an afternoon, not in a week, but much less elementarily. So she shows that you may endow FPI, we can extend it to a model of T. And she uses the infinite subfields of FPI RPXC. I mean, it's a cute little paper. There is a little error, but they have also, we fixed it. I think we could fix it. I mean, it can be linked this. Okay. So that was a starter. So early on, in 89, she had this paper. Now, a cornerstone of the theory of pseudofinite fields is this result from 92 due to Zoe, Lau, and Angus. And it is a generalization of Langevin, but two formulas. So you have a ring formula, phi of xy, x and y are tuples. And then there is a finite set of pairs. So the first is for the dimension, so it can go from 0 to the dimension of ambient space, 0 to n. And the second element comes from the positive rationals, or you have 0, 0. This will be for the empty set. Such that we also have a constant, which depends on the formula, such that for every finite field FQ and every parameter tuple B, you can plug in. So the formula phi of x, y stands for, y is the parameter variable, so phi of x, b, you can evaluate for b in FQ, you can evaluate this in FQ, you can count. So it's like, if it were an absolute irreducible variety, you would be in the Langevin situation. Now you have an arbitrary ring formula, and then they show that actually there is this finite number of pairs, so that you have the similar count as in Langevin, just that this time, put at this. sorry. Can you manage? There is mu. So you have a multiplicity. You have a dimension and a multiplicity. And moreover, this is important also to prove, the set of B's for which you fall into one of the classes is a definable set. It's self-definable by a formula from the language of Hils.
The rational is not implied the mu?
It is always rational. It can be rational, yes. You will see in a second. You can think about it already. Think of the squares. Yes, because I think of the squares until I get it. So let's see. I mean, of course, since I have these constants for Q large enough, the cases are destroyed because I can no longer have these two in both processes anymore. So for large Q, depending on the constant I choose and the pairs I choose, I get a partition in the cases. Yeah? And so let's get to examples. Yeah, the first example is the old example. If my formula expresses I am in x is in the epsilon value, the epsilon is absolutely integrable, the integral. Okay, so the of dimension d, then I can just take d, 1 by Langevin. So the multiplicity is 1, and the dimension is d. And the constant comes from Langevin. Yeah, so far so good. Now, this is for offer, yeah? So you have take the squares. Yeah, so my formula doesn't even need the parameters, I just have x. So the formula says I'm a square. Then of course you need two things, 1 and 1/2 and 1, 1, depending on the characteristic. But that does it. Okay. And let's give a little application, and just to illustrate, so this is also one of the first I gave you the paper to explain. So you can prove non-definability results using such, because it is a big restriction on how defined the set can look like. For example, you cannot uniformly define for infinitely many defined powers Q with a single formula or instances of the same formula. You cannot single out FQ inside FQ squared, because the growth rate would be logarithmic. So it's just that, I mean, there are many non-definability results. And in a way, we're saying that this is a nice back and forth. So you use Langevale, Arcs use Langevale to prove the characterization of pseudofinite fields. There you eliminate quantifiers. There you work in infinite models. There you find, using the, of course, I need heavily the quantifier reduction, they need heavily the quantifier reduction to get these rational numbers. Basically, everything is not so far from being squares. You have some fiber size and so on, so you can divide by fiber size. That explains the rational numbers you get. But then you work in these infinite models, and then at the end you can go back to the finite world and you get somehow a Langevale effect like Langevale, boom, boom, and then you get back to something like a Langevale. Yeah, but you need to go through the infinite to have access to quantifier reduction. Okay. Now, probably, no one can forbid us that you also look at such formulas in infinite models of the theory of finite fields. So let's do it. So let's take a pseudofinite field. Let's take this as a ring formula. Since we know that for large Q, we have a partition, we must have a partition for infinite finite fields, so for pseudofinite fields. Namely, so if you take your parameter B, I know there is a unique d mu, because this is true for all Q large enough, and so it's in the theory of all large enough finite fields, so it's true in pseudofinite fields. So I find exactly one of the finitely many pairs d comma mu, such that it applies. So this is nice, because now we have a notion of dimension. So we can say this d is my dimension, so d is the dimension of x, and mu is like a multiplicity. Yeah. For example, the squares would be dimension 1, but say in a pseudofinite field of characteristic different from 2, it would be multiplicity 1/2. And this, of course, this has extremely nice properties coming from counting. Everything, I mean, is preserved under definable bijectivity. Of course, it must be preserved by definable bijectivity because it's true for finite. And since everything comes from finite counting, nothing can go wrong. Also, the dimension, in this sense, is equal to the dimension as an algebraic variety of the Tarski closure. Show this. And then, of course, the dimension of the union is maximum of the dimensions. And if they intersect trivially, they have the same dimension, multiplicity is add. This comes all from finite counting. It's true in the finite, it must be true in the infinite as well. And if one has larger dimension than the other, then the growth rate is negligible, so you just keep the multiplicity of the one with larger dimension. This also follows immediately from looking at the growth function. And there is Fubini, because it's true for counting. So if you have a definable map between two definable sets, and say if the dimension and multiplicity of the fibers is constant, e comma nu, say, dimension e, multiplicity nu, then you can determine the dimension and the multiplicity for the total space. Because, again, true for finite.
So this is related to some odd work on Galois that we
It is related, yes. But it is a final version of quantifier reduction to look at that. They say so, and so on, yeah. Yeah, I mean, yeah. Yes. And so you can do that. We also want to talk about measures a bit later on. Trivially, you can do now the following. You can normalize at a given definable set. So let X be a definable set of dimension D, non-empty of dimension D, and measure nu. Then you can take the definable subset of X, and you get a measure on them, which is a probability measure on all definable sets, just by taking, if the dimension is smaller, the measure is 0. If the dimension is the same, then you take the ratio of the multiplicities. And this way, you get a finitely additive probability measure on subsets, definable subsets. And at the end of the talk, the second to last part of the talk, I will talk about the measure devised by Zoe and Nick Ramsey. And, yeah, So this was very influential, this counting theorem. And for example, Dugald and Charlie Steinhorn devised and took it as axioms for a framework, and they call these measurable structures. And also, yeah, that's one branching off. Another one just is doing pseudofinite monotheory and doing pseudo counting there. Very active and very prominent in recent years. And let me add one thing here. So let's take the normalized. So this is the definition: normalized coarse dimension. I take a family of finite structures Mi. I take an ultra product M, which is infinite, and I define for every internal subset. So in particular, for every definable subset, X, which is then an ultra product of Xi's, you can define delta of X is the normalized coarse dimension. You just take the limit according to the ultra filter of the logarithm of the size of the set Xi divided by the size of the set of the structure itself, Mi. And this is either minus infinity if it's too often zero, empty the set, or else it will be something between 0 and n. Because if I take the full set, I get n. And it has, of course, many nice properties, again, coming from counting. Yeah, and it's a version of Rubini, and it's invariant under definable bijections, which directly comes from the fact that it's a limit of finite world. And let's look at this in examples of pseudo-finite fields. We see that we get back the dimension of x in this way, but we lose a lot of information. We only get back the exponent. If you take the count we had for defining sets or finite fields, it was mu approximately mu times q to the d, but the mu disappears in my logarithm counting. I only retain the d. Okay, so I do this for some reason because I wanted to mention a result I spoke about in December. This was maybe the first GTM, Zoe could not come to the talk. She came to the lunch though. Last time I was here in December, and I also had dinner with her at home, but she didn't see me talk about it. So let me mention this result here. Let's look at finite difference field. So you have a finite difference field is in particular a finite field. So let's say fp to the ni, and we have a difference operator. So every automorphism of a finite field is of the form Frobenius to some power. So let's take it to the mi, to the mi. And we're only interested in special regimes, so namely the size of Frobenius, so to say, goes to infinity. So the limit of p to the mi is infinity, according to the ultra filter. And also the index of the field goes to infinity, so ni divided by mi goes to infinity. And let's look at such difference fields. So now we are almost back to difference fields from the last part. So an ultra product of these creatures, very different from a modular case today. Now let's define a second quantity. We already have defined normalized coarse dimension. We can use it here. A second quantity, transformal dimension. It was implicit in Udi's talk. So if you have a partial type over K, take pi, you can take the maximal transformal transcendence degree of a solution in some elementary extent. Well, in the same way, you can define Zariski dimension in varieties. Here we so maximal transcendence degree of a solution, and here we do it for transformal dimension. And so this is second quantity, and in a recent work with Udi Hrushovski and Pinchan, so we proved that for a quantifier free partial type. So this is the logic there's not much logic. There are no quantifiers, but the logic is used in the proof. Or one of is used in the proof. But if you take a quantifier free partial type, and the infimum of the formulas in the type, or the infimum of the coarse dimension of the solution set type, so the left quantity, is equal to the minimum, and this is equal to the transformer dimension. So in some sense, it's maybe the expected value, but so this is a recent result, which is a little bit in the spirit of this, not the spirit of pseudofinite counting. And what does it use? It uses an effective version of Langmuir, especially bounds that are polynomial in the degree of the variety. That's the most important one. And as heavy ingredient, recent work of Yuval and Udi Hrushovski on why those valued fields endowed with non-standard properties. There is a critical theorem on stable embeddedness and purity of the residue field, which we need to get to grips with smoothness, local dimension, because we can use valued fields. A strong topology is easy to work with locally. You can locally say what the dimension is. Statistically, you can't do this. It's the same, they mean the same, but you have to work in valued fields, and then you want to forget that you use the valuation on defining a certain set. So that finishes almost the first part, but I want to mention that there's a lot more, by the way, on pseudofinite trees. So Udi mentioned, though, that let me debrief. In their work, they give a precise account of the imaginaries in pseudofinite trees, because they also discuss what do we need to name if we don't have a generator of Galois. Then you have certain, certain algebraic imaginaries you can name, so that then you have already elimination of imaginaries in pseudofinite fields without this extra structure. There is another paper, Özlem Beyazlan, a continuation, I think, of work of Özlem and Udi, where they study Galois groups in pseudofinite fields, but in sets containing a model. And surprisingly, very often, these are trivial. So surprisingly, once you work over a model, UCI is equal to ACL. Surprisingly, to me, it's very surprising. So this is another work I will not talk about. And also this work that appeared on the slide by Tamara this morning, I think. But this paper just appeared in JSL, I heard, or was accepted. So where she studies non-existence of prime models. So there is never a prime model. If you take a field which is not already pseudo-finite, it will not have a prime model in the category of finite. And she generalizes it to kappa prime and so on under PCH. I'd like to move on. So amalgamation, I think this is maybe the hot the deepest things Zoe did in PSC fields. I cannot give any account which would do justice to what she did. So let me just try to say a little bit of things. So it is closely related to, well, let me say, for example, simple theories. They generalize stable theories, and many key results from stability can be lifted to simple theories. For example, in the study of groups and generics, it's more complicated to work with them, but still things are very nice. And the abstract development of simplicity is intimately related to difference fields, I mean to the theory ACSA in particular, and also to PSC fields, because these provide extremely nice and also important algebraic examples. And Zoe is at the heart of this all, so to say, or was at the heart of this all. Now let me just briefly define what simplicity is. So you don't have complicated families of definable sets in a certain sense. You don't have this. This means the tree property, which means you have one formula, phi of x, y, and you have a tree of parameters. I plug in for b. So b eta is an infinite branching tree of infinite depth. You don't have these, so that below every node, let me draw this. So this is right here. This is maybe phi of x e eta, and you have below you have phi of x e eta 0 and so on. Yeah, then phi of x e eta 7, and so I want that in this horizontal line, for a given k, always, this is inconsistent whenever I pick k instances, and at the same time, we want consistency through paths. So this should be consistent, this should be k consistent. It's a bad behavior, you can encode complicated objects, and if we don't have this, then we are simple. So no formula has this bad behavior, the theory is not simple. Now there is a theorem which is very nice for algebraic examples. It also gives us a shortcut for discussing this. So it's due to Anand Pillay, which tells us that a theory is simple if and only if there is a very nice notion of independence, namely automorphism invariant on small subsets of a monster model, which satisfies a certain number of properties. It's symmetric. It has full transitivity, so A is independent from CD over B if and only if A is independent from C over B, and D is independent from A over BC, hyperspaces. It has finite character. It doesn't matter whether on the left or on the right because I'm symmetric, so let's take this one. A is independent from C over B if and only if I have a finite subset of A, this is the case. Local character, if you have a finite set A0 and C an arbitrary set, then you find a small subset, namely one of size at most the cardinality of the language, so that A0 is independent already over this C prime. So you cannot have incredibly many reasons for being dependent. Say, there's a bounded number of such. It has extension properties, so every type, so here the type of A over B has an extension to BC, which is independent. That means I find a realization A prime having the same type as A, so that this is independent. And finally, and this is the key, the rest will be always obvious in examples, I would say. But the last one is this independence of over models, which corresponds precisely to three amalgamation. In Udi's talk, if I add the condition that I want to be dependent, so if you add there that you're going to be linearly disjoint in the fields example. So how does it read? If you have a model, and you have A and B extending the model that are independent, so here, A and B are independent, and you have two tuples C1 and C2. C1 is independent from A over M, C2 is independent from B over M, and they have the same type over M. So potentially you can amalgamate this type, or actually you can, and there is a C which realizes the union of these two types, and moreover is independent from the union. This is maybe not the best way of phrasing it. Free amalgamation, which is equivalent, is a symmetrized version of this. So it's equivalent to what Udi drew on drawing. There you have somehow, this is maybe A, this is B, and this C. I mean, it comes as a C1 over here, it comes as a C2 over here, but the same C, because the whole thing does not exist yet, and then we have the existence of the whole, and that gives me the C. So it's completely equivalent to the amalgamation. Independence of. And moreover, if you have such a notion, then it must be not fucking independence, which I will not define here. So for those and we have already seen this in Udi's talk, this language associated to a profinite group. I present it slightly differently, but it's equivalent. So Anand Angus Macintyre, I just take, for every natural number n, I take as a sort the quotient by open subgroups of index at most n. And since there are finitely many groups of cardinality at most n, I have to say this up to changing, up to putting finitely many sorts into one. It's the same framework as what Udi has used. So you add this sorts, yeah, take the disjoint union of all G mod n's where n is open of index, open and normal of index at most n, little n, in a profinite group. And then you add relation symbols you need to understand the situation. So you add, for example, one expressing membership to the same. Yeah, so we are from the same G mod n. You add the ternary relation talking about the graph of multiplication, that all three come from the same. And you also compare them between smaller and larger n. So you know these things. And that's all you need to make. And this is a way to incorporate the absolute Galois group in the structure that we can think of more theoretically. And the definition, an arbitrary field is called bounded if for every n it only has finitely many separable extensions of degree n. Equivalently, the Galois group has only finitely many open normal subgroups of index at most n for every n. That's some trivial algebra equivalent. So equivalently, if I look at the structure given to the profinite group, all the sorts will be finite. Namely, will be algebraic over the implicit. But this explains why the situation is much easier fitting the Galois groups if you're bounded.